Welcome to the last session of the day, which is a session on AI and ICT applications. So we have 3 papers to be presented. And the first one is from Vitaliy Kobets. And the title is An Hybrid Approach to RFM Analysis Integrated Reinforcement Learning, Clustering and Classification for Dynamic Customer Segmentation. So, Vitaliy, the floor is yours.
Thank you so much. So, dear Chair, dear participants of AI session of Victory Conference, let me introduce my research, hybrid approach to RFM-D analysis, integrating reinforcement learning, clustering, and classification for dynamic customer segmentation, prepared by me and my colleagues, Dmytro Volyk and Yevheniia Spivakovska from Kherson State University. Here you can, next. Yes. So here you can see a structure of my presentation today. And analyzing and segmenting customer characteristics are key for creating and developing effective business strategy for selling products, especially in turbulent market. Using machine learning methods to study customer behavior allows businesses to adjust their offers and marketing strategy more accurately to customer preferences. One of the most promising approaches to this area is RFM-D analysis, which allows customers to be classified by frequency, age, amount of purchases, and other indicators. However, with development of technology and accumulation of a large amount of data on marketing transactions, traditional analysis methods are not always able to take into account all the nuances of customer behavior, which necessitates the search for new approaches to more accurately segment customers to create personalized offers of goods and services. Modern researchers actively uses various machine learning methods, including reinforcement, unsupervised, and supervised learning. These methods can significantly improve the accuracy of segment classification and customer behavior forecasting and adapt customer interaction strategy depending on changing market condition. However, no comprehensive studies currently combine these methods for effective segmentation and customer interaction optimization, which is why this study is novel. The goal of this research is to develop a customer segmentation approach which integrates machine learning techniques and adjusts it to dynamic market conditions for personalized customer interactions. To achieve this goal, we have following main tasks. Apply RFM-D analysis. RFM-D means recency, frequency, monetary, and diversity to open transaction data sets. Use K-means clustering to group customers based on RFM-D metrics. Implement reinforcement learning methods to optimize customer interaction strategies. Apply supervised learning methods to forecast customer behavior, and visualize the experimental results and provide recommendations. This study applied methodology to segment customers more accurately and optimize market strategy. First, we selected a data set of 10,000 customers described by 4 key behavioral features: recency, frequency, monetary, and diversity. This extended RFM-D model provides a foundation for behavioral analysis. Second, we performed data pre-processing. Recent values were imputed using the median method. Futures were normalizing using minimum and maximum scaling, and outliers in frequency and monetary metrics were deleted to stabilize model performance. First, we applied several segmentation algorithms such as gradient boosting, XGBoost, light general boosting model, Cummins, etc. We used supervised ensemble learning methods to improve classification accuracy and behavior prediction. Fourth, we incorporated reinforcement learning techniques. Specifically, Q-learning was used to adjust customer interaction strategies dynamically. This method allowed the system to learn from past actions and to make optimal decisions to enhance marketing effectiveness in real time. Fifth, we evaluated model performance using several metrics: accuracy, mean square error, mean average error, R-squared, and correlation metrics to detect multicollinearity and ensure robustness of predictions. Sixth, we introduced a module for price elasticity estimation using logarithmic transformation. Based on this, individual discounts were dynamically calculated. This discount strategy ensures that the increase in sales volumes exceeds the price reduction, leading to an overall increase in customer check value and network profit. Finally, we used Python for implementation and for result visualization. In recent research, customer segmentation relies on demographic or behavioral data and integrates geographical, psychographic, and benefit-based factors. This multidimensional profiling enables personalization, which is more precise and improves long-run retention. In this case, the classic RFM model, where was used only recency, frequency, and monetary, remains one of the most commonly used segmentation method. However, it has limitations. It cannot effectively capture textual preferences, fails to distinguish between short-run and long-run customers, and overlook diversity in product choices. Enhanced model like RFM-T, where we can add times, for example, for cohorts of customers, and RFM-G, where we can add diversity, has been introduced to address this. The RFM-G model enables the exploit identification for customers with varied product baskets and a high potential for cross-selling. Regarding segmentation algorithm, Cummins clustering is widely applied, often preceded by RFM scoring and outlier removal to enhance accuracy. The elbow and silhouette methods determine the optimal number of clusters. Modern approaches combine RFM-G-based segmentation with machine learning techniques such as support vector meshing, nearest neighbors, trees, naive bayes, and LLMs. So these methods are used to process customer survey data for more precise clustering. Recently, reinforcement learning methods such as Q-learning and deep Q networks have gained popularity in segmentation. These methods allow real-time adaptation to dynamic market conditions by learning the best strategy to engage different customer groups. So the analysis allowed us to distinguish three key customer segments. So in this case, these three separate segments is indicated using customer ID. So in this case, buyers with high frequency and high variety of purchases. In this case, you can see it selected in the left side of this slide, has low recency, indicate active interaction, and high values of frequency, monetary, and diversity. It suggests what these customers are most valuable, for example, for this retail or for this online shop. The next one, buyers with high purchase and low variety, high values of recency and monetary, and low frequency and diversity indicate low loyalty and activity for customers. It's a bet for our supply chain. And at least third group, it's active average level buyers. Average values of recency, average frequency, and average diversity indicate potential loyal customers. So in this case, preliminary processing of our data can give us some conclusions about who is in our data set and how can we process our data on the next steps. So we start from unsupervised learning. In this case, they applied the Cummins algorithm to segment customers based on recency, frequency, monetary, and diversity. The elbow method suggested the optimal number of clusters is 4. In this case, you can see two graphs. The left graph indicates principal component analysis, and the right graph indicates TSNE method, where we can see that exactly 4 different clusters of customers we can visualize. So in this case, cluster 0, it's the largest group. Frequent purchase and diverse product choice. It means that in this case, we can choose discount for this group. Cluster 1, high spending and diversity, but small group. For this, there is no discount because it's switchable for exclusive offers. Cluster 2, low purchase frequency, often one-time big orders. In this case, discount can stimulate their 2 active purchases. And at least cluster 3, average behavior, steady profit, non-sensitive to price change. In this case, people buy, then goods or service are needed for them, regardless of price. So in this case, no discount is supposed. Personalized pricing results based on previous clustering and price elasticity. So after clustering, we identified different purchase drivers for each group. In this case, cluster 0 and cluster 2 are highly sensitive to discounts. Cluster 1 values product variety. Cluster 3 includes customers who buy only when necessary, regardless of price. For example, you can see table for some customer with separate ID. He or she made 7 purchases because data is anonymous. Personal discount were applied, then price elasticity increased compared to previous check. Discounts were given only on purchases number 2 and number 6. Then price elasticity increased, resulted in 15.7% discount and 17.4% discount correspondingly. And after that, total average check increased by 676 euro per this period. Supervised learning. These models were trained to predict personalized discount levels based on client characteristics. Target variable is discount, and predictors are recency, frequency, monetary, diversity, and cohort month. In this case, XG Boost outperforms our others because it has minimal MSE and MAE metrics and maximal R-squared. You can see also cohort profitability. You can see that until 7 cohort, our profit remains almost unchanged. And after that, we can see what cohort in other months is increased. And the maximal revenue from customers we can see in 12 cohorts in this data. So, discount effects on customer behavior. In this case, for example, higher discount means more frequent purchases. So we consider different levels of discount, 10%, 15%, 20%, and 25%. And in each case, we can see that frequency of purchases increased. In this case, we can see a right connection between these 2 variables. The next one, increased average check value with discounts. So in this case, we can see the more discount, the more monetary, so the more average check of each consumers. Recency, customers return more often after receiving discounts. So the more discount, the more frequent purchases. And at least diversity, wider product variety purchased when discounts are applied. So we can see that very high discount, 25%, means a very big diversity of goods and services. These effects make discount beneficial both for sales growth and for customer retention. The next method, it's a reinforcement learning. So key results of reinforcement learning analysis. Reinforcement learning was applied to determine the optimal discount level for each customer segment to maximize company profit. The agent adjusted the discount level based on customer characteristics. Impact of discount on RFM-D parameter. Recency. So in this case, almost unaffected by discount level. Customer return after similar time periods regardless of discount. Frequency. Medium discount slightly increase the number of purchases, indicating this is the most responsive parameter. Monetary. Spending amount is stable across all discount levels. Discounts have little effect on spending volume. And diversity. Product variety purchase remains almost unchanged across discount categories. So frequency is the most influenced for discount levels in this case, and recency, monetary, and diversity are largely unaffected, indicated limited value of discounts beyond frequency simulation. For reinforcement learning, we have some important correlation metrics where we can see strongest correlation are observed between frequency and diversity, making them the most meaningful for segmentation and targeting. Recency is less correlated, but still useful for detecting inactive customers who may require reactivation. So highest profit is obtained from cohort 1, in this case, followed by a sharp decline and stabilization. So discount should primarily be used to boost purchase frequency. And in this case, personalized discount strategy adjusted to cohort behavior are essential to avoid unnecessary revenue loss. Reinforcement learning, Q-learning, compared to ML methods, gives us some insights. Q-learning adapts in real time, learns customer behavior and adjusts strategy dynamically, delivers the highest profitability by optimizing discount per client. So the best methods among supervised, unsupervised, and reinforcement learning was in reinforcement learning, taking into account metrics of profit in this case. Conclusions. The first one is reinforcement learning creates adaptive and profit maximizing strategy. Reinforcement learning agent dynamically adjusts real-time discounts level based on customer behavior. The second one is K-means and XGBoost enhance personalization and segmentation. K-means effectively clusters customers by behavior using elasticity to fine-tune incentives for each segment. And XGBoost, in this case, accurately predicts optimal discounts for each cohort, enabling targeting marketing strategies. Third is combining RFM-D with machine learning methods improves loyalty and revenues. Integrated machine learning approaches personalize interactions, adapt to customer sensitivity, and optimize discount, leading to increased profit and better customer retention. Using all three machine learning types allows us to cover different levels of the segmentation problem. Clustering for discovery, classification for prediction, and reinforcement learning for strategy optimization, forming a customer engagement framework. Thank you for your attention.
Thank you. So we have time for question. Yes.
Thank you. Thank you for your presentation. I'm a little bit curious about the limits of applicability of the approach you presented today. As I understood from the presentation, it is based on retail industry, supermarkets, and open data. So the spectrum of goods is those which are normally present in supermarkets, right?
Yes.
Would it work similarly, or wouldn't it work at all with the different goods, different methods of retailing, bulk sales, or whatever? What are the limits of approach?
Thank you very much for your very good question. Yes, our data was obtained from Kaggle platform, so the platform with open data, and in this case we tried to apply all three methods to compare results, and in this case we reveal that each of these methods can simplify decision making, and from a high level of decision making, when we understand which difference between our customers segments, till individualized discount for each of them in each clusters. So in this case, applicability of this method depends only on open data, because to apply this analysis, we can know some main features. For example, the last purchase, the average check of each customer, and in this case, how often each customer buy the products, and diversity, how many different goods in one check simultaneously can be for one purchase. If we have this data, we can apply all these three methods.
Still have one more question, if I may.
Yes.
Okay. My second question is about the data set. You mentioned that this is a public data set you downloaded from Kaggle. What would be a minimal statistically representative data set of this sort to draw reliable conclusions? Thank you.
Thank you very much. So in this case, we choose between different data sets, and these data sets was chosen because each contains 10,000 observations, and in this case, this data is aligned to normal distribution. So we can apply different methods from linear till non-linear methods. And in this case, the number of observation was primary features which we use to when we selected this data. Thank you.
Thank you, Vitaliy, for the comprehensive presentation. It's really practical results. And I just, you mentioned you use open access platform. And my question is, could you recommend, or do you know open access platform or resources that includes Ukrainian open resources that we recommend our students?
Thank you for your question. In this case, we really used open access data on Kaggle platform, and in this case, we didn't detect about Ukrainian data sets, but it's possible because this data is anonymized, but the main problem of this data is maybe that it's not last data. So sometime from 3 to 5 years expired after this data is opened and anonymized, etc. But in this case, when we need data, in this case, Kaggle platform is one of the most powerful platform where we can get access to data with very different characteristics. So you can try to find using keywords with Ukrainian data sets.
Okay, thank you.
Thanks.
More questions? We have five minutes more. If you have, so maybe I have one. You mentioned that you combine different techniques of machine learning and I'm wondering if you have some kind of according to the objective you have for creating this classification of customers. Do you have some methodology to apply this technique at a certain place in the whole process?
Thank you very much for your question. So in this case, we use it such supervised methods as for example, XGBoost. In this case, this method was the best, due to which we can classify all our customer with minimal errors. And in this case, XGBoost was primarily unsupervised method, which using metrics such as mean average error, mean squared error, R squared, was selected as the best classification method to differentiate our customers.
Okay. No more question? So thank you.
Thank you for your attention.
So we are the next speaker maybe is online. It's about Maryna Nehrey. No, I think she's Maryna Nehrey. Petro constructing the optimal temperature trajectory. Yeah.
This is the updated version.
Petro. Okay. So Petro is here. Okay. Welcome, Petro. So Petro, you have your slide in the, okay. So Petro will tell you something about the constructing the optimal temperature trajectory from the wheat vegetable cycle. So thank you, Petro, and we are hearing you.
Just a second microphone.
Ah, yes. You don't have. Take this.
Thank you. Good day, dear colleagues. My name is Petro Hrytsiuk. My co-authors Maksym and Maryna Nehrey from National University of Water and Environmental Engineering in Ukraine, in collaboration with ETH Zurich in Switzerland. I will present our research on constructing the optimal temperature trajectory for the wheat vegetable cycle in the steppe zone of Ukraine. Grain production is a key sector of Ukraine's economy, meeting domestic food needs and ensuring a stable inflow of foreign currency. Between 2019 and 2021, Ukraine's grain output averaged 75 million tons. However, yields fluctuate considerably, largely due to variable climatic conditions. Uh, our, um, our objective to determine the optimal air temperature at each stage of wheat vegetable cycle in the steppe zone of Ukraine. Data collection. Our observation period for agroclimatic conditions spans only a few decades. Given major structural changes in agriculture over the past 30 years, we use data from 2000 onwards. During this time, large-scale agroholdings have become the dominant producers of grain in Ukraine. Due to war, some April 2022 data were missing and replaced with expert estimates. Regions with similar climate features were grouped into agroclimatic zones, allowing for larger datasets in machine learning analysis. The main were growing season lasts from April to June. We analyzed 10-day average temperatures and monthly precipitation totals, noticing that precipitation is highly localized and generally less correlated with yield than temperature. This is characteristic data collection, a definition of variables, and summary statistic of numerical features for steppe region. T1, T2, 10-day temperature for vegetative cycles of wheat yield, of wheat. Model. First model, this is a linear trend. The trended yield is defined as difference between yield and linear trend. The trended yield X is a function of climatic factors. In this study, we only took into account the dependence of yield on temperature. The effect of climatic factors on plant growth highly nonlinear. This reflects the existence of an optimal ecological niche for each species. So too low and too high temperature can reduce yield potential. The effect of climatic factors on plant growth is highly nonlinear. They reflects we built a quadratic regression model using the 35 highest yield samples in our data set. We removed statistical insignificant factors to produce the final model specification. Quadratic regression model, a factors model, all significant, and R square 0.97. We then applied cross-validation to test the model predictive performance and to ensure robustness and forecasting. We see an 3 increase, which is a good result for such test, RMSE error. Constructing the optimal temperature trajectory. Table 6 lists the coefficient of objective function obtained from quadratic regression model. These parameters of the objective function are the temperature T, Y, each constrained but it observed minimum and maximum values. These bounds list in table 7 define a domain T in the 9-dimensional temperature space. The point corresponding to maximum wheat yield located in this domain. The F's objective function, this is quadratic regression. Table 6 coefficient of objective function, and table 7 limiting of factors this model. Next, we finish the stationary point of objective function. We take the first partial derivatives of the function 1 and equate them to 0. From condition 3 and table sim, we determine coordination of the stationary point. 4. Coordinate of stationary point. To determine two coordinates of the maximum objective function, we follow this algorithm. Case y less 0 and by great 0. Yes, in result, following this algorithm, we determined the following coordinates of the maximum point of the quadratic objective function. The optimal temperature trajectory is presented in figure 1, solid line. Dashed line indicates the corridor observed temperature. Analysis of the figure, we can see the temperature near the midpoint of the admissible range favorable for wheat growth during the early stage of the growing season, where lower temperatures are preferable in the final stages. To improve the temperature trajectory, we applied additional machine learning methods. Random forest or support vector machine algorithms. Combining this method with differential evolution algorithm yields a hybrid optimization approach where the machine learning model acts as a predictor and DE function as meta-heuristic optimizer. Main steps of this process. First, the machine learning model, RF or SVM. Next, the bound for the parameters T1, T2 are defined. And the DE algorithm then generate a population of parameter vectors which evolve through selection, mutation, and crossover. Each individual in the population is evaluated using the objective function, and the best performing solution are retained. And can we see figure 2 methods. The solid line shows optimal temperature from the quadratic regression model, thick dashed line from SV method combined, and dotted line from the RF method combined. Dashed line indicates the corridor observed temperature. Main result. Wet yields in Ukrainian regions show an overall upward trend, but with substantial fluctuation driven mainly by climatic variability. The quadratic regression model explains yield fluctuation with an accuracy of 97%. Using multivariate function optimization, we defined the coordinates of the yield function maximum as an alternative hybrid approach, combined random forest and support vector machine models with the differential evolution algorithm. This method leverages the full dataset and offers greater flexibility in locating the yield maximum. Optimal trajectories such as that moderate April temperatures and the relative temperatures in May and June are most favorable for high wet yields. Thank you. Thank you. A question, please.
Thank you. So we have time also for question. Yes, please.
Thank you for your research, and I have a few questions. The first, my question is not about technical side of your research, and because it's more about sense of this research. First, my question about steppe region in which you made your observation. It was North Steppe or South Steppe region, Middle Steppe region. It's very important because whole steppe region have a different limitation factor. And for example, in South Steppe, the most limitation factor for yield crop, for productivity, is wealth, is amount of water resources.
Thank you. We use data from the 6 region of steppe zone of Ukraine. Climatic factors for us is
Maybe I a bit clarified my question. My second question is, have you considered the impact of precipitation or rainfall, amount of rainfall for crop yield? Because it's really, this factor has greatest impact for crop yield in steppe zone.
yes, impact on rainfall is great, but in one locate great, other locating small, and this factor
Yeah, I absolutely agree because, for example, I was born in steppe region in Kherson, and in our region, we sometimes said that if you have 3 rains in May, the agronomist no need. And that's why this is my question about this region in which you provided you observe, and about impact of this factor. Thank you.
Thank you. Thank you.
More question? Yes.
Thank you. Thank you for a great presentation. Could you please show your model once again? Slide 10 to 12, I believe. I'm asking about the model. Yeah, yeah, here. This is the general representation of your regression model. What are the T's? Why do you have this so many T parameters? T2, T5, T3. What do these T's mean?
All parameters 9 linear and 9 quadratic, 18.
What is the sense of this
Sample 35 samples. 35.
35 samples of what?
Yes. No.
Is it about temperature? Is it about daylight? Is it about precipitation?
10-day temperature for 6 region, and 9 stage of vegetable cycle.
So this T2, T3, and so on, T99 is different measurements of temperature?
This is significant factors. T2, decade of April. T3, 3 decade of April. T5, decade of May, and other.
Does your model distinguish the geographical position, for example, this region or that region?
graphical illustration. Six region data set for six region.
So-
Six region, 22 years, 25 for years, 25 6, 115 samples. All.
I'm not asking about the number of the samples. I'm asking, yeah, you know, if you come to Provence in the second decade of April, it will be plus 24 or the like. If you go to Nottingham Hill, it will be plus 13. So there is a huge difference. Ukraine is a big country. So if you go to the north steppe, as our colleague mentioned, you will have lower temperatures. If you go to the south, you'll have higher temperatures. Does your model account for that?
From data, we can see higher and low limit of data. Stage 1, first decade of April, 2 decades of April, 3 decades of April, high limit and low limit.
To have a distribution in
Data, from all data.
Okay, it's
Just corridor.
all the eggs in one basket. Thank you very much.
Thank you.
Region mix in the same data set. No, there is another question here. And we have time.
Hello. If you have just said you built a quadratic model, yes, is it reasonable that your model has no any products of different teeth in the model? Thank you.
No, yes. This model is not simplified. Why your products, this model very, very unsimplified. We don't. Quadratic, yes, quadratic model simplify and critical point light find product no.
Okay, more question? So I have just one question. Your model is almost based on the temperature, which is a parameter which is based on the climate, so you don't have any action on it. Can you imagine mixing some other parameters that you can act on? Like, for example, the humidity, maybe by putting water on more water on the vegetation, or fertilizer, or things like that. Do you think?
Yes, I agree. Yes, I agree. No, next stage our work. Yes.
Okay. Okay, so thank you for the presentation.
Thank you.
So now the last presentation is in a completely different domain. Is in the domain of CPS, cyber physical system, and the timing analysis of such a system. So it's presented by Pavlo. You have your, okay, Tokariev. And it's about the comprehension of the timing behavior of service-oriented architecture in software-defined vehicle. You can take this? Is it open?
Okay.
Yes, this one. Okay. Thank you, Pavlo.
Thank you. Okay, hello, everyone. My name is Pavlo Tokariev, and I'm a postdoctoral researcher at INRIA Université Côte d'Azur. And today I would like to present our work, which we did in the context of a European project called Half SDV. And our work is titled Understandable Timed Analysis of Service-Oriented Architecture Components in Software-Defined Vehicle. I will start directly with the explanation of what is a software-defined vehicle. So far, the car architectures went through several iterations of its architecture, ranging from the distributed to a highly centralized zonal architecture, which I think is going to be or already being deployed. In the distributed case, we have a big number of electronic control units, each responsible for their small subsystem of the car, which then are connected with the bus. In that architecture, to develop any application, essentially we would need to disperse the logic of the application on these various devices, which creates a tight coupling between the software and the hardware and the application that we're developing. On the other side, we have the centralized architecture. There we can develop the application as one singular unit of software. But because we deploy it in a few places, there are much more functions running at the same time, which creates a contention in resources. So we have to share the resources, and that can create contention between them. As for the SDV itself, what it proposes is to abstract away the physical architecture of the vehicle with a hardware abstraction layer. From the point of view of an application, it means that we can no longer rely on specific characteristics of the vehicle, which means, can be difficult, but if we are able to do that, we're able to create portable applications. And so we can deploy the same application on different vehicles. And another really important feature of SDV is that we want to deploy new features or update the existing software even after we deliver the vehicle to the customer. And of course, portability of the software helps in that. But of course, if we do this abstraction, it creates some problems. And from the point of view of application, the problem appears in a way of uncertainty. For example, for its execution time, even if you compute how complex is your program is algorithmically, if you deploy it on a certain platform, depending on how many resources there are and how many other applications are running, what their priorities are, it's not given that you will execute in a specified time. And the same situation is for the communication with the environment. So the sensor data needs to pass through the whole architecture of the vehicle physically and through all the layers of the software abstractions up to the application and back if there's anything to command to the environment. When we are developing an application, we just don't know these values, and this creates an uncertainty. And of course, an SDV car is still a car. And so it's a subject to requirements, safety requirements, and so timing constraints. And we want to verify these constraints early because it's, well, the earlier we verify the requirements, the easier it will be to develop and cheaper. So our proposal in this work is to formalize the temporal behavior of hardware abstraction layer and of application. And using that description, we provide an timing analysis and appropriate feedback so that the designer can improve on their design. And during this presentation, I'll use a running example of automatic emergency braking system. So the goal of the system is to avoid or mitigate collisions. And it's doing that by, first of all, projecting the path of the vehicle into the future and segmenting it into zones using so-called time to collision. So it's a value depending on the speed of the vehicle. And so basically, if the time to collision is too big, well, we don't care, we don't do anything. If there is some object in close to the vehicle, but it's still not dangerous, then we warn the driver. And if the object is too close, we brake automatically. If you would want to implement the system, you'd use architecture like this. So you would collect the information about your environment with the sensors. Then you would fuse that information into the same representation with data fusion. Then you would identify the objects. You would compute the time to collision, and then you will make the decisions if you need to, well, to do anything. But in this presentation, I'll use a slightly even simpler version of this system where we just use one sensor and one actuator, so a brake. And I will segment them in 3 components. So the radar, the brake, and the controller, where the controller has all the logic of the application. Now, the architecture basis of software-defined vehicle is service-oriented architecture. There we have essentially the components. The components can read and write data from ports. The components declare or require some ports. And when the components end a hardware abstraction layer, and when the components, one component is required a port and another one is providing it, then we connect them. And the way that the hardware abstraction layer declares what ports does it have is by using vehicle signal specification. So it's a language that provides a data model to the signals of the vehicle. Essentially, it describes the hierarchical structure of what the signals should be present in the vehicle. And there are characteristics such as data types, units, and category as sensors or actuators, which are basically say as how we should access the data, or we provide the data or we read the data. And that language also has a standard catalog. So basically it's a list of sensors, signals that can be present in a vehicle, and then the manufacturers are supposed to provide implementations for that set. Another important aspect that we use is of function chains. So in our case, it's basically a sequence of component activations. It starts in a sensor, and it represents a stimulus to our system. It ends in the actuator, and it represents the reaction to the stimulus. And then the role of the function chain is to define a causality chain between these two events. So for example, we start in the radar, then we pass the data to the controller, and the controller decides and pass the data to the brake. And then if you would take the start and the end of the function chain and you make a difference, then that is the reaction time of the function chain. As for the actual proposal, we define a domain-specific language in which we specify which VSS signals the hardware abstraction layer provides. We define which components application has and how they interconnect. We specify the timing annotations on the components on the VSS signals and functional chain specifications. And we do timing analysis, extracting reaction time, waiting time, and resource waste related to the functional chains. And finally, there are several assumptions that we make in the semantic of our framework, is that we assume that there are infinite resources in our system. And when we communicate with the hardware abstraction layer from the application, that's instantaneous. As for the timing annotations itself, first thing that we specify is triggering rules. These are essentially say when we start executing in the component or the signal. So periodic is, I think, self-explanatory, but even triggered, it starts the execution of the component when data is available at a specified port. And so given that, the sensors from hardware abstraction layer can only be periodic and actuators can be both. Then when we specify the components or signals as periodic, we need to specify the period. And all of the components and signals needs to have a latency or execution time. And on top of that, we add uncertainty. So for periods, it's a jitter. And for execution time and latency, it's best case and worst case. And of course, it's not exactly reasonable to assume that in the range of uncertainty, you can get any value with the same probability. So we assume that there's given also a distribution. In our experiments, we always assume there's normal. And just to demonstrate quickly how the uncertainty would look like for different cases. So this is a certain period with jitter. Here we can see that the period of 5 milliseconds and the jitter of 0.5 millisecond. And the start of the execution of our component starts somewhere inside that range. The similar idea is with execution time, but instead of the start, we vary the end of the execution. And then if we combine the two, we get pretty chaotic system. And here I have noted that what would be the earliest and the latest executions that you can get in these two cases. And if we would simulate our running example, and we would take several cases from the start, then it would look like something like this. Now let's look at one case from that simulation. So here I have overlaid the function chain. And so you can see that the start and the end define the reaction time. When we have the data ready at the controller, but the break is not yet being executed, we have to wait. And that creates a waste of time, which we indicate with waiting time. And from the perspective of the functional chain, the actuations of break, which could not receive the data from the functional chain, are considered useless. And this is a form of waste of resources that, again, we extract with our analysis and present to the designers. As for the analysis, it's summarized here. There we start, of course, with the description of the system in our domain-specific language. So we specify the VSS signals, components, annotations, the connections, functional chain. Next, we obtain temporal traces. In our case, we do simulation. First, we were using a Python library called SymPy, which is a process-based discrete event simulator. But we have slowly moved to using modular real-time clock constraint specification language, which is my language that I developed in my PhD. But what it allows us to do is, because it's a declarative language, we can quickly experiment with the semantics of our system. Yeah, simply that. But to obtain temporal traces, we are not obliged to use a simulation, and we can use the monitoring of the actual system. Then from the functional chain description and temporal traces, we obtain the reaction time, the waiting time, the useless actuations. That was the first branch of the analysis. In the second branch, we generate a model. We're doing that by first translating the DSL into timed automata. Then from the timed automata, we translate it into label transition system. From the label transition system and the temporal traces that, again, we get them from the simulation, but we could get them from the actual system. We obtain a probabilistic transition system. And from the probabilistic transition system, we can query, again, the useless actuations, but these useless actuations can be selected more precisely in the model. We can access the overall waste of resources, not from the point of view of the individual functional chains, but overall. And we also can access what would be the coverage of our simulation. So if we have a simulation that does not cover the whole state space, we can ask ourselves, is it a correct simulation? Do we have requirements that are too relaxed? And so we need to add more requirements to our system, etc. And then we reconciliate the analysis. And I will show you now how. So to remind you, in the running example, we have two periodic signals of radar and break. They have periods of 150 and 100 milliseconds. And we have a controller with execution time of 50 milliseconds plus minus uncertainty. And we have a requirement that the reaction time should be less than 120 milliseconds. So if we would run our analysis and we would plot the reaction time distribution, we will quickly see that we do not satisfy the requirement. So what we could do, we could reduce the execution time of controller, and we could rerun our analysis, but in fact, it does not change much. So it pushes a bit the reaction time to the left, but we still do not satisfy the requirement. The second thing that we can do is to look at the waiting time. So I remind you that this is the time between when the controller stops executing and the break executes. So when it actually consumes the data. And we can see that in both of the cases, we wait at most 100 milliseconds. And so if we could reduce that number, we should be able to improve the reaction time. And if we do exactly that, so we reduce in the third configuration actuated period from 100 to 50 milliseconds, and we get a noticeable reduction in reaction time. But there are still outliers that are bigger than 120 milliseconds. You can see them barely here. But if we combine the reduction in actuated period and reduction in the execution time, we obtain the result that we were looking for. But of course, when we reduce the actuated period, then we execute the actuator more, and this wastes resources. So to conclude, we have designed a framework which is based on service-oriented architecture with timing annotations that are aware of uncertainty. And we describe with that the software architecture of SDV. Then we use that description to analyze our system, and we produce metrics to that analysis that can be actionable for the developer. And as for the future work, we would like to, first of all, integrate our timing annotations to the VSS standard itself, so that the VSS signals will have the timing annotations with them directly. In the project of HAL for SDV, there are several use cases that they want to use to demonstrate how useful the approach is. And of course, we would like to integrate into that. Next is that when we do the reconciliation at the end, it's still a manual process. We would like to automate it and present it as hints in the code editors, so that people who are do not have a PhD in computer science can still understand what to do. And of course, we want to remove our assumptions that we made about the resource usage. And of course, immediate communication. And that's it.
Thank you, Pavlo.
But if you want to see the experiments, you can go and see it on the GitHub. And we're also hiring for this project. So if you want to work as a software engineer or a postdoc, you're welcome to go by these links to see the positions.
Good to know. Okay.
Thank you.
Thank you for your very detailed and interesting presentation. I would like to ask you about beginning of your presentation. You talked about different type of architecture, centralized and decentralized one. So the question is, which type of architecture did you choose and why?
So thank you for the question. It's not me who chooses the architecture, and kind of the SDV can work with any, because you abstract away the architecture. But I think the idea of the manufacturers is to use the centralized architecture, because you're supposed to actually deploy the software, and it's easier to do when you have not a lot of components.
I see. Thank you.
Thank you.
Okay. More question? No? I have one about, if I remember, I need to remember my question, who comes. Okay, so you have this architecture which is based on software-oriented architecture, which introduce delay when you call a service in such architecture. You have a delay. Is this delay correspond to what you call your waiting time in the analysis?
No.
The waiting time is the time when you ask for computing something.
The waiting time occurs when. Thank you for the question, first of all. No, the waiting time occurs when you have a periodic component. And when you have a communication with that periodic component. So if other component ended inside of that period, you have the waiting time before the next component in the functional chain will actually execute.
Okay, so the part which correspond to the SOA calling and the time need to call the service is not explicitly integrated as a parameter, or is it embedded in the execution time? Or
you mean in the transition, like
yes, when you
where it takes to send the request?
Yeah.
No, this is for now. It's the time is 0, so it's immediate.
Okay, and after you simplify the initial example by just focusing on one sensor and one computation and one output. What's happened when you have multiple computation inside your controller? And what's the impact on the timing analysis? Is it easy to compose with?
What happened? What happened is that
are you able to tackle the fact that you are multiple?
Yes.
Multiple execution in parallel, and in this case, how do you compose them? Is it in parallel? Is it sequentially? Because you mentioned that you have an infinite resource number.
So the parallelism question depends on how the components are triggered. So if they are triggered periodically, then it means that they possibly can be in parallel. But if they are even triggered, then it means that they have to be in sequence.
Okay. So in this case, the timing.
So yeah, in event triggered case, the overall timing basically means the sum of the two executions. But when you have the periodic ones, you can have the gaps like a waiting time here.
Okay. And I have a last question. You mentioned that you can move, you can modify, you give feedback to the engineers by saying that you can change the period or the execution time, but generally this information, these requirements come from the engineer themselves. So what does it mean? What action should be done by the engineer in this case? What can so when you say, okay, you will have, you will comply with the constraint if you divide by 2 the reaction time, or by modifying the periodic triggering of sensor.
Yeah, but I think the primal requirement is the reaction time. Is then you arrange everything else
Okay.
to satisfy the reaction time. And so in this case, we think that you have a slack to choose from and
Okay.
to demand from the platform.
Okay. More question? No? It's okay. So we finish 10 minutes before the time. So thank you, Pavlo.